Good. Let's continue. So in this case, our first step will be to determine the SN curve for the notched specimen. Our first step will be to model the notch effect. In this case, they gave us the theoretical stress concentration factor. That's what they've given. Stress concentration factor, Kt is equal to 2. They gave us the ultimate tensile strength. That was also given to us, right? And the notch root radius was also given. That is what was given by the problem. To model the new SN curve, we have to calculate the SN curve for the notch specimen. Control V, this comes from your notes. Let's make it a little bit smaller so it fits in there. So, in a nutshell, this is the unnotched specimen, the blue line, but we need to drop the SN curve to this point by looking at the factor that we have, the fatigue factor, at 10 to the power 6 cycles, which is, so the point that we have there for the unnotched specimen at that point there, SE is equal to 0.5 ultimate tensile strength. That's for 50% probability of survival. And remember, that's for a rotating bending specimen. Then we need to drop the curve further to this point here by the notch fatigue factor, the fatigue notch factor that we're going to calculate now. The same is done here. At 1,000 cycles here, we have the fatigue strength for 50% probability of survival for a rotating bending test, complete reverse stress amplitude of 0.9 ultimate tensile strength. But then we need to drop it for notch sensitivity by the notch fatigue factor Kf accent. And that's what we're going to calculate now. If we go back to our notes, the equations are as follows, our formula sheet. Our formula sheet gives the following equations. It says the fatigue notch factor, Kf, is given by this equation here. And then we have these approximations for alpha in the equation. Now we're going to work with millimeters, so we're going to use that approximation. And then, of course, there are also other approximations for alpha according to different rules. I'm just going to use this one. Eventually, when you apply, you can use different ones. So let's copy these equations to our notes, to our problem, so that we can apply it there. So this is what I'm going to use. So for this, we have the following equations. Control V. So this is what we have. Notch fatigue factor at 1,000, at 1 million cycles. So first thing that I'm going to do, at endurance limit, which is also at 1 million cycles. This is the factors that are applicable. Control U. Now let's calculate it. in this case, we have a notch root radius equal to 4, but we first need to calculate. So in this case, we can apply this equation here. So our value for alpha will be equal to exactly what we have there, Control C, but we will use 1050 here for sigma u, 1050 for sigma u there, and this calculates to, now I'm just going to do this quickly in MATLAB. Let's do this quickly in MATLAB. So I'm just going to bring my MATLAB window here, make it small, so that we can perform this calculation right here at the bottom. So here we have 300 times 6.89 to take it to MPa, divided by 1050 to the power 1.8, and then we multiply this by 25.4 to get the answer in millimeter, but remember there's a 10 to the minus 3, so multiplied by 10e by 1e minus 3. Right, and my answer is 0.086. So here we have 0.086, and that's in millimeter. Right, with that answer calculated there, I can now go and calculate my fatigue notch factor at endurance limit. Now I can have my Kf, and my Kf will be equal to 1 plus, now what is Kt was given was 2 minus 1, 2 minus 1, divided by 1 plus alpha is 0.086, divided by R, which is 4 millimeter, and this works out, shift enter, works out. Let's do this in MATLAB quickly. So in MATLAB, we will have then Kf is equal to 1 plus 2 minus 1 divided by 1 plus 0.086 divided by 4. And that's 1.98. 1.98. We expect the notch fatigue factor in this case to be very close to the theoretical stress concentration factor, and the reason why we expect that is because of the high tensile strength. So that's why we expect these to be very close to each other. Let me put an enter in here so that I can align these at the equal sign. Good. Now we need to get the fatigue notch factor at 1000 cycles. Control U, fatigue notch factor at 1000 cycles. And if we go to our formula sheet, this is what we have in that case. Kf accent is given by this equation, and it's given by this sheet here. So what I'm going to do is I'm going to copy all of these to our sheet so that we can apply that, so that we can calculate the fatigue notch factor at 1000 cycles. So this is what we have. Just to put the figures in the center. Now, for us to do this, we first need to look at, you can see that the notch fatigue factor here is, the notch sensitivity factor here, which is this factor that you see on this side. You can see that it's a notch sensitivity factor for 10 to the power 3 cycles. It's very sensitive to the ultimate tensile strength. Now, in this case, our ultimate tensile strength was 1000 MPa, so 105 MPa. I'm just going to put a little thing here on the sheet. So in this case, we have sigma U. Sigma U was equal to 1050 MPa, and that is equal to 105 MPa divided by 6.89. So let's do this quickly here. 1050 divided by 6.89. That gives us 152 KSI. 152 KSI. Right? Let's make this little block clear so that you can all see it. Let's just fill it and make sure it's a box that can be clearly seen. Or let's move it a little bit up there. Let's move it to there. Right. Now, for this, I'm going to draw a line now at approximately, this is 100, this is for steel. It's a steel part. So it's 100, 110, 20, 30, no, 120, 40, 50. 120, 40, 50 is about approximately there, 150. And 152 is approximately there. So I'm going to draw it there. It's approximately that value there. And then I'm going to insert horizontal line that goes from that value to there to the left. And we can see that this factor, if that is 0.3 and that is 0.4, 0.35 is approximately there, and 0.35, it's a little bit more than half between 0.35 and 4, so we can approximately say 0.38. Now, so from the figure above, we have this equation here, Control C, Control V, equal to Q, which is equal to 0.38. If you look at this factor here. So from this, we can say KF accent is equal to 0.38 times KF minus 1 plus 1. And we know KF is we have it here at the above. KF was calculated as 1.98. So here we have it equal to 0.38 times, now 1.98 minus 1, 0.98 plus 1. And this is equal to 0.38 times 0.98 plus 1 is 1.37. 1.37. And this is the factor with which we're going to drop the SN curve at 1,000 cycles. So this curve here, this point here will be 0.5 SUT divided by KF. This will be 0.9 ultimate tensile strength divided by 1.37.